All right, so let's, in the last few minutes here, to go through the internal energy balance. Right. So in internal flow, as I mentioned before, we have this consideration where the mean temperature is changing as a function of position. You have to solve for that mean temperature profile as a function of position. So we're going to do that the same way we've done that for everything else. We're going to use a control volume analysis and go through that process. And then you end up having this relationship where you're solving temperature as a function of position, and then you can use that along with whatever convection correlation or friction factor correlation that you want to use for those situations. Okay, so let's come up with an energy balance for flow in an internal setting. So let's say we have a duct here, and we have flow coming in this direction. So what we want to do is let's think about all the thermal contributions here that are going into possibly raising the temperature of this bit of fluid that's moving through our control volume. So let's draw our control volume. First of all, I'm drawing the control volume over the entire area of cross-sectional area of the duct. And again, I'm doing that because I'm gonna make somebody else basically solve for what's happening at the wall. If I did this in 2D, then I'd be solving for gradients as a function of y. I'm just gonna say punt that problem to somebody else. And we'll have a correlation that we use for that, instead of directly trying to solve for it ourselves in our control volume. Okay, so we have what energy coming in here is going to be, mass flow coming in, we'll say that's m dot. We have enthalpy coming in. We're going to use enthalpy as I. You can't use H for obvious reasons. We'll use I, so that's going to be mass flow coming in at enthalpy I at position X. This thing is, we'll call this dx wide. Leaving, we have m dot I at x plus dx. And then let's say we have some heat flux coming in from the duct into the control volume. And that's going to be, we'll call that q dot double prime s times the area that's available for heat transfer in this node, which is what, perimeter? The perimeter of the duct times dx. It's the area available for heat transfer on this control volume. Okay, we are in this making some assumptions. Other sources of heat in this could be generation, right? Maybe this is a reacting flow. We'll ignore that. Let's say that there's viscous dissipation, that is heat generated due to shearing of the fluid. Let's assume that's small for this. You do that, justify that calculation with viscous dissipation being negligible as what, Eckert over Reynolds, I think that was what it was. That's much less than 1. Let's see, let's also assume this is incompressible. Let's also assume that there's no possible heat conduction in the axial direction, that there's no significant conduction from one control volume to the next. It's just heat that's being added. So all those are usually really good assumptions. By the way, they're for most flows, we don't have to think about those things. Okay, so we have this. Let's write out. Let's see, our energy balance is going to be what's coming in. So q dot double prime s times perimeter times dx plus m dot I at x is equal to m dot I at x plus dx. Expand that out as we always do. Q dot double prime s perimeter dx plus m dot I at x is equal to m dot I x plus d m dot I dx times dx. Right, so then let's see, you can cancel out this, cancel out our dx from both sides then. And we're left with our final ODE, which is q dot double prime s perimeter is equal to m dot times d I dx, d enthalpy dx. So really simple ODE here, but it just comes from solving what's happening on the fluid. And so maybe not something that we really thought about before. We're just going to take the fluid temperature as a given. But it's pretty straightforward to do this. So we can also write this equivalently if this is an incompressible fluid, we can use the specific heat in place of the enthalpy. And then we would write it as, let's see, Q dot double prime S times perimeter is equal to M dot times C Tm dx. So specific heat C. And keep in mind, we're doing this in terms of the mean of bulk temperature. So we're solving for the bulk temperature, not the temperature at any individual position. This is the average, the velocity average temperature is a function of area. So this is what we're solving for. So this is really useful if we know what? If we know Q dot double prime S. Sometimes, we don't know the flux. We know the temperature. So if we wanted to write this in terms of temperature, we would just write it as perimeter times, what's the rate equation here? So dH times Ts minus Tm is equal to M dot C dTm dx. Okay, so those are these two things here. Box here. These are equivalent. They're equivalent statements. I'm not making any judgment about what's constant and what's a function of x here. You'd have to decide that when you get into it. So if you decide that Q dot's a function of x, maybe that's something you have to factor into the way you solve the ODE. You can use numerical methods to solve this. You can use analytical methods. This kind of depends on how hard the problem is. Okay, so let's go through, just quickly solve for the case where we have constant heat flux and a case where we have constant temperature. And you'll see how this ends up looking in practice. Okay, so first let's do the specified heat flux. Specified flux. All right, so that was Q dot double prime S perimeter is equal to M dot C dTm dx. So I need to solve this for temperature, Tm. That's the thing I'm trying to solve for. I'm assuming Q dot double prime is S. S is specified. I'm not necessarily assuming it's constant, but I'm assuming it's specified. So let's go through and separate this out. So we have, let's see, on the left-hand side, let's say we have our Tm, so we'll say dTm. We're going to bring all the x stuff and the constants over to the other side. So that gives us a perimeter over M dot C times Q dot double prime S. And again, that could be a function of x. It doesn't have to be constant, times dx. We can add dx over. So then I'm going to integrate, right? This is temperatures on the left, everything else is on the right. So I'm going to integrate this. I'll integrate the right-hand side. And we'll integrate this from, on the right-hand side, we're going to go from 0 to some position, x. So our expression we'll end up with is in terms of x. And then that corresponds to what? Like my temperature at x equals 0 is what? Temperature at x equals 0 is going to be T in, over the free stream temperature coming in. And then the temperature at position x is going to be Tm. That makes sense? We're going from 0 to some predetermined position x. Doesn't have to be L in each position. That corresponds to this is kind of a way of enforcing boundary conditions through the integral. Okay, so we do that integral and we end up with following. We say, here we have Tm. It's going to be Tm minus Tn. Let's bring the Tn over to the right-hand side. So Tn plus perimeter times the perimeter over M dot C times, given this integral. So all I've done here is just take care of the left-hand side. Okay. If the special case where the heat flux is constant, it's a single value, then this just becomes, if Q dot double prime S is constant, then this just becomes the thing we're familiar with. which is, let's see, would be Tm is equal to Tn plus perimeter over m dot c times q dot double prime s times x, right? Pretty obvious. But okay, this is maybe somewhat interesting in that we have this linear relationship between the position x and the temperature. So just a way of solving it. If we plot this out, what does this look like? It will look like this, where let's say we have coming in here Tn, let's say, so coming in Tn. So if I plot the temperature, the mean temperature of this fluid is saying right away, immediately I'm specifying my flux. That doesn't change as a function of heat transfer coefficient or anything. It's just a specified flux. That's going to go to increasing the mean fluid temperature. And so the fluid temperature is going to look something like this. You're going to have a linear increase in mean fluid temperature. If I want to get the surface temperature, my surface temperature is going to be, it's going to be H times Ts minus Tm is equal to Q dot double prime S. So if I have specified a surface flux, that H is actually changing quite a bit as a function of position. So it's infinite at the leading edge. That means my surface temperature at the leading edge is going to be the inlet temperature. And then you're going to see a rise. And at some point when the flow becomes fully developed here, XFD, then that temperature difference between these two streams becomes constant. And so that's going to be your surface temperature. So this is Ts, this is Tm function of x, right? So this is what your temperature profiles are going to look like in the T. So, okay, so that's for the heat flux. So I think we're out of time. If you're curious about the specified surface temperature, it basically looks like, what did we draw the first time? It looks like this, right? And this solution, I'll just give it to you. I'll give it to you right here. So it's Tm is equal to Ts minus Ts minus Tn times exponential of minus perimeter times x times h bar over m dot c. Okay, so that's the solution for this constant temperature situation. Okay, that's it for today. Thanks, everyone.